In this video, what I will explain is about what is the V curve and inverted V curve for synchronous generators. So, uh, in the previous lectures, what we have seen is we have seen the equivalent circuit of synchronous generator, and based on the equivalent circuit we have written a equation which was for the terminal or the voltage per phase. So the equivalent circuit which we saw was per phase, and if you have VA is the voltage which is available across, or VA is the phase to neutral voltage at output for phase A. If this is VA, then the equation can be written as EG A plus J into IA excess. So this is the equation for VA, where EGA is equal to the voltage generated in phase A, and excess is equal to XAR plus XL, which is also known by synchronous reactance, where this was due to the armature reaction and this was due to the leakage reactance of the winding of A phase. Then what we also saw in the previous lectures that the power could be given as the power developed, or the power developed by the A phase at the output could be given as VA into EG divided by XS into sine delta. This was a case when XS was very large than the RA, and this is for the round rotor machine. So if this is my first equation, this is my second equation, then it is possible to say that if I am having a constant power operation, when my power output is equal to constant, then it could be said that my EG sine delta is equal to IA excess cos phi is equal to constant. So these are some of the assumptions which I want to make, and this has been already derived in the previous lecture. But the thing here is that the V curve is a graph, or a graph between my current per phase, or the IA, and the field current IF. So the graph between these two is that is the IA and IF graph, is known as the V curve. So again, uh, from the equation of the EMF, it can be said that EG is directly proportional to my flux, and my flux per pole. So if I'm having a round rotor machine, then the flux per pole is directly proportional to my IF, or how much is my field current. So by varying the field current, or by increasing the field current, it's possible to increase the flux, and by decreasing, it's possible to decrease the flux. So again, what will happen is that based on your flux, your EMF will, or the EG voltage which is generated, will increase. So EG will decrease when my flux will decrease, and in this case the IF will increase, and in this case the IF will decrease. So this is one another thing which I want to consider while before going for derivation of the V curve, or going to show how it is possible, or how it is possible to get the V curve in a synchronous machine which is round rotor. So one more thing is that when my flux is increasing, or in this case, when I am considering this case, when my flux has increased and my IF has increased and my EF has increased, this has increased to such a level that it is greater than the terminal voltage or VA voltage. So if this is greater than the terminal voltage or the VA, then the machine is said to be in a state which is known as overexcited field. And when my flux is less and my IF has been reduced and my EF, which is now less than what is my VA, then the machine is said to be under excited state. So these are some of the considerations before deriving, or before going to explain how it is possible to get the V curve for the machine. So considering these basic things, now the next thing which I want to explain is that going for a graph considering the state where my EF has been greater than VF, which is overexciting, and my EF is less than VF, which is underexciting, and both these cases is for my phi flux has been increased, and in this case my flux has been reduced, my IF has been reduced, and my IF has been increased. So what will happen now is, if I plot a simple graph by taking the VA voltage as the reference, so my power output given by P out is equal to, for phase A, is equal to VA into IA is equal to constant. So my VA is also not changing, my IA is also not changing. So if I take this state and if I draw a straight graph, this is which is not to scale but to represent, and it's possible to show the same graph to scale and validate it. So if you are having a VA, and now in the first state you are saying that your IA, and that is your power factor phi, which is, so your case 1 is phi is equal to lagging, So this is a under excited condition operation. So now you can draw a constant power line, and if this is your O, then whatever is my voltage generated, which is given by Eg plus Ia into excess of J, this gives what is my Eg, and the line which on which it lies will, this is my power line. If I am saying this, then this is for if I am to keep my power constant. Now if I am increasing the so for case 2, which I am taking, my phi is equal to leading now, but I am not changing my Ia. My Ia is same and my voltage is also same. So for the same amount, whichever is this, if I am drawing it, this is my Ia now with a leading power factor. And if I am drawing graph, which is, if I am drawing a line which is passing through, and if whatever is my Eg in this case, if this is my Eg1, this is my Eg2, so, and this is what is Ia into excess. So the angle here was delta 1 and the angle here was delta 2. So it's seen that delta 2 is less than delta 1, and so, which in the case where it was overexcited, so in the overexcited state there is a reduction in delta, while in the underexcited state, so this is just to show the two cases. Now if you see the two cases, then it is possible to say that there is some definite relationship between my field current and my Ia. So if you consider the same equation, If sine delta is equal to Ia excess cos phi. So based on this, it can be said that my If is equal to, or my Ia is equal to If sine delta divided by excess into cos phi. So if you are substituting the values here, then you will, what is varying here is my delta. So your delta has varied from delta 1 to delta 2, while the other thing that varied was your flux or your power factor. So for this case, the power factor we have taken leading and lagging was same, but the delta was the other thing which varied here, and the Ia is constant, so there will be not much change happening in your excess also, since your synchronous reactance XAR is directly proportional to Ia. Since your Ia is changing, the excess will also have some effect. But based on this equation, it's possible to get a curve for the relationship of Ia is to If. or IA and IF, a relationship between IA and IF. So this curve is known as what is known as V curve for the machine or the synchronous machine. So it is based on this equation, and possibly, as you can see, the delta 1 will vary for as my IF will change, increase or decrease. So this is what will give rise to what is your V curve for the machine. So it's just taking an example of the equation as IA is equal to IF sine delta divided by excess of cos phi. So now I'm simply taking an example in the case. Now what I want to show here is that if my IA is fixed, I'm not varying my IA, my P output is equal to fixed, I'm not varying my P output. This is for per phase, and for phase A I am considering here. So now the big question here is that these two things are fixed, and I am considering two cases here. My one is case 1 and the other is case 2. In my case 1, my power factor is 30 degree lagging, and in case 2 my power factor is 30 degree leading. So now if I am substituting it here for the value of IA, and based on my IF in the first case was equal to 1.2, which was under excited state, and so 1.2 into sine of a delta which I am going to consider here is 20 degree, sine of 20 degree divided by 0.2 of cos 30 degree. So this will give rise to what is your 1.2 into sine 20 divided by 0.2 divided by cos of 30, which will give rise to what is your IA is equal to 2.36 amperes. And again, if you keep the 2.36 as constant and 1.2 into sine of delta, and now if you vary this same thing into cos of minus 30 degree, so in the second case what I have done is I have increased the IF to a value of 2.4 amperes, and just taking a consideration, this is a overexcited state, and in this state the delta which I am getting is equal to 9.80. So this is my delta 2, and the delta 1 was equal to 20 degrees. So there is a change in the delta. So for the same IA, I will get two values of IF, one which is lower and one which is higher. So this will give me a curve which is like a V shaped, and If I am considering the state where my machine is loaded to a 50%, then it is seen that this loading is equal to 50% is what power output I have kept constant, is equal to 50% of full load. And so correspondingly I will get two value for the same IA. I will get two values of can be achieved from two values of IF. So this is how my IF will vary, or the field will vary, and this is how my IA will vary. And it's possible to get higher curves as the power is being increased, and it's also possible to fix these curves for a specific kind of power factor. In the specific case was equal to 0.8. So this kind of curves which you get is known as the V curves, and this is a curve between the IA and the IF, where the IA is a current per phase of stator. So again, if I'm considering the same equation where my IA is equal to IF sine delta divided by XS into cos phi, and this was for the case where my RA was considered very less than what is my XS, so I have neglected my RA, and this is for round rotor machine. So again, if I consider the same equation in terms of my cos phi is equal to IF sine delta divided by XS into IA for the same equations, and if I plot it for different values, then the curve which I get is a kind of inverted curves, and this curve between the power factor is equal to 1, and with the increasing power factor and with the increasing of IF, so this kind of curves are known as my inverted V curves for synchronous machines or generators.